Hello trigonometry students, my name is Jamie Emigh and this video starts our discussion on chapter 7. Title is Applications of Trigonometry and Vector Applications. Let's talk about an oblique triangle first. A triangle that is not a right triangle is called an oblique triangle. The measures of the three sides and the three angles of an oblique triangle can be found if at least one side and any two other measurements are known. How is that possible? The law of sines. In any triangle ABC with side lowercase a, opposite angle capital A, side lowercase b, opposite angle capital B, and side lowercase c, opposite angle capital C, then the following is true. The side length lowercase a over sine of the angle opposite it is equivalent to this ratio. The side length lowercase b over sine of angle B, which is equivalent to this ratio. The side length lowercase c over sine of the angle C. And notice that I am emphasizing the lowercase and the capital. These formulas are case sensitive, as all formulas in mathematics. So make sure you are being careful with your lowercase versus capital letters. Okay, what I would like you to do right now is take this triangle right here, and I want you to label capital A, capital B, capital C, lowercase a, lowercase b, lowercase c on the triangle in such a way that you can use the law of sines. I'll give you a hint. These ones, the capital ones, they need to go on the angles, okay? These should go at the vertices of each angle. And these should be opposite their corresponding capital letter on the side lengths. These represent side lengths. Okay, pause the video and please label this triangle with ABC and ABC now. Welcome back. If you came up with your capital A and across from that is your lowercase a, your capital B is an angle, across from that is lowercase b, and your capital C is an angle and across from that is your lowercase c, then you came up with one correct solution. There are two more correct solutions, and that would be as long as you keep capital A at an angle, and then let's pretend we moved capital A to here. Then opposite of that, the side length would be represented by lowercase a, and then we can move this one to be capital B. Across from that would then become lowercase b. This one we could make capital C, and across from that would be lowercase c. So there is a second solution, and there's one more solution that would work. Let's make this one, oops. Let's make this angle right here capital C. Across from it would then be lowercase c. Let's make this one right here capital, what haven't we done yet? A. Across from that would then be lowercase a. And if we make this one over here, let's see, this would have to be B. Across from that would then be lowercase b. So this is another possible solution, or possible correct way to label the triangle so that the law of sines can be used. And I said there were only three, but now I'm thinking, oh, there actually would be more. We could swap, leave A right there, we could swap C and B, that would work as well. Leave B right there, we could swap A and C. So there actually, I did the combinations, but if you count how many possible permutations, there are other arrangements. All are correct as long as our capital letters are on the angles or vertices, and our lowercase letters are opposite their corresponding capital letter, and they are representing side lengths. All right, moving on. Here's an example. We're asked to solve the oblique triangle ABC. What does oblique mean? If you said that it is not a right triangle, you are correct. All right, and so looking over here, yeah, this is definitely not a right triangle. This could not add up to 90 degrees. Or this right here could not measure 90 degrees, because then our triangle would not, interior angles would not measure to 180. Okay, so to solve the triangle, we need to find all of the missing parts. So we have 2 angles given, 1 side length given. So we need to find another angle and 2 more side lengths. So we've got 3 pieces to find. Let's use this first cell here to find lowercase b. To find lowercase b, we would want to use the part of the law of sines, the first ratio equal to the second ratio. And I'm just calling them first and second because in the theorem here, it's this ratio equal to this ratio. You can put them in any order. So using this ratio equal to this ratio is a good strategy because we know lowercase a, it's 42.9. We know capital A, 32.0 degrees, and we know capital B, 81.8 degrees. So what we've done here is translated from a geometric figure into an algebraic equation, and this equation right here has only one unknown. And that is oftentimes our goal. This makes us happy because when we have an equation with one unknown, we have a lot of tools that we can use to isolate and therefore solve for that one unknown. All right, one move we could make right here would be cross multiply. So our 42.9 times sine of 81.8 degrees is equivalent to sine of 32 degrees times lowercase b. Then divide both sides by sine of 32 degrees, and we have isolated lowercase b. At this point, I want you to pick up your calculator, make sure that it is in degrees, and type this in from left to right, top to bottom. And if you do that correctly, approximate to the nearest tenth, you should get 80.1 centimeters. All right, now we have found one other part of our oblique triangle. To solve the triangle, we need to find all 6 parts though. So we got 2 more to go. All right, the next one I would go for is the measure of angle C using the triangle angle sum theorem. That is that all of the interior angles of any triangle must sum to 180 degrees. It's A plus B plus C equals 180. This is a good formula to use strategically because we can isolate lowercase c, which is the only unknown, because we know A, we know B. Isolating c gives us this here, and accurate to 1 decimal place, well, this one's actually equal to 66.2 degrees. All right, so we found another part. Almost there. We have to solve the right triangle. We have to find just the remaining lowercase c. All right, strategies to find lowercase c. It is a side length. So I'm thinking pick a part of the law of sines that includes lowercase c. So that would be, I'm going to go with this ratio, a over sine of a equals c over sine of c. You could go with b over sine of b equals c over sine of c, but this would be a, this selection will maintain more accuracy because if we choose the ratio with lowercase b and sine of b, we would most likely be using this approximated 80.1 centimeters, which would lose some accuracy in our final answer, could potentially lose some accuracy based on how many decimal places we round to. So I'm going to go with lowercase a and sine of capital A because we know their exact values. And I'm going with lowercase c and sine of c because we are being asked to find lowercase c, our goal is to find lowercase c. So we need an equation that has lowercase c in it. All right, beyond that strategy, this is, or beyond that, the benefit of that strategy, this is a good choice because we know lowercase a, we know capital A, we know capital C, and just like that, we have translated from a geometric figure into an algebraic equation that only has one unknown. Cross multiply and divide both sides by sine of 32 degrees. That will isolate C for you, for us. Then pick up your calculator, make sure it is in degrees, type this in from left to right, top to bottom, and you will get approximately 74.1 centimeters for that last side length of our oblique triangle. And this was all done using the law of sines and the triangle angle sum theorem. Next, we have the area of a triangle formula. And you may think, well, we already have the formula for the area of a triangle. It is 1/2 base times height. And you are right. 1/2 base times height is one formula for the area of a triangle, but there's a part of it missing that we just overlook when we're first learning it, which is fine. And that is that if the included angle is 90 degrees, well, sine of 90 degrees is equal to 1. And we end up with our area of a triangle equals 1/2 base times height. Let me elaborate on what this included angle of 90 degrees, making sine equal to 1 means. In any triangle, capital A, capital B, capital C, the area is given by the formulas. Area is equal to 1/2 one side length times another side length. We're used to that part right there, except normally it's base and the height specific to that base or altitude. So we're used to this already. 1/2 one side length times a different side length multiplied by sine of, and notice it's the capital A. So if we have lowercase b and lowercase c, it has to be sine of capital A. That is because capital A is the angle included in side lengths B and C. Here, I'll sketch that just really quick if you're wondering. That would be lowercase, capital A, capital B, capital C, lowercase a, lowercase b, and lowercase c. So see here, if our selection is lowercase b and lowercase c, that would be this side and this side. The angle included between those two sides is right here, capital A. So see how the first formula has lowercase b, lowercase c, and capital A. All right, next one, area of a triangle is equivalent to 1/2 side length A times side length C times sine of the included angle B. Third one, area of a triangle is equal to 1/2 side length A times side length B times sine of angle C. And then back to our note. If the included angle is 90 degrees, sine is 1, and we get to our area equals 1/2 base times height. Let me elaborate. Let's take this as, let's make it the first one here, okay? So if we make this B, and this will make C, and we multiply that by sine of 90 degrees, that means that we are working with a right triangle. It would look like this. If the 90 degrees is here, that would be our capital A. This would have to be B, and this would have to be C. You see here, side length B, side length C, included angle capital A, okay? If this is 90 degrees right there, we know that sine of 90 degrees is equivalent to 1. So this right here would just become a 1, leaving us with 1/2 B times C times 1. Okay, multiplicative identity, we don't need to write that anymore. So we would be left with 1/2 B times C. And as we can see here, that if C is the base, then B is the corresponding height because we are working with a right triangle. So this is, let me erase that pen and just rewrite it. This is how we first learned it, but it's actually these three formulas. We kind of overlook them. We start with this and then we build up to these right here, which makes sense with the natural learning process, starting with a little bit simpler formula. Okay, let's look at an example. Find the area of the triangle ABC to the nearest square foot. Okay, so we have many formulas now, well, 4 for the area of a triangle. We have 1/2 base times height. We have this one, and this one. So we need to be strategic. We need to select one of our 4. This is not a right triangle, at least I don't believe it is. So I'm not going with this one here. All right, I need to label these to make my selection. Across from capital A, I would write a little lowercase a equals 34.0 feet. Across from capital C, I'd write a lowercase c equal to 42.0 feet. And across, well, we have the measure of capital B as well. It is 55 degrees, 10 minutes. We haven't worked with those in a while. That's part of a degree. Okay, so using what we have, which is little a, little c, capital B, select the correct or the strategic formula that we should use. If you went with this one, nice job. That would make sense because we know this, we know this, we know this, leaving our formula with only one unknown, capital A, which is what we're asked to find. Plugging in little a, little c, and capital B, this is what we have here. At this point, pick up your calculator, type this in, make sure you're in degrees, type in from left to right, and careful with this part. We haven't done this since chapter 1, but we need to type it in a sine of 55 degrees and 10 minutes. If you type that in correctly, approximate to the nearest square foot as requested, you should get 586 square feet. If we're given the lengths of 2 sides and the angle opposite one of them, then there are 0, 1, or 2 such triangles that may exist. Think about that. Given the lengths of 2 sides and the angle opposite one of those sides, maybe it's impossible to construct a triangle. 0 triangles may exist. Maybe there is one unique triangle that you can create with those 3 measurements. Maybe there are 2 such triangles that you can create with those given measurements. This situation is called the ambiguous case of the law of sines. Starting with this angle here, capital B would have to lie somewhere along this side if a triangle exists, because capital A is here, capital C is here, so capital B would have to be somewhere along this side. Well, if we have an acute angle A, then 0, 1, or 2 triangles could result. And here it is in a table showing the options. 0 triangles would exist if sine of that angle B was greater than 1, because that's outside of the domain. I like the visual sketch better. See here that if little a is too short, basically, there's no way you could connect it from vertex C to some vertex B along this side. And that's okay, that's fine. It just means that there are no triangles that would exist with those particular measurements. Here we have 2 cases where 1 triangle would exist, and that is if sine of B equals 1 or sine of B is somewhere between 0 and 1. I like the sketches better, like I said. Here you would see that if A is equivalent to H, then this 3rd side would connect C and B. That would actually form a right triangle. And if A is greater than or equal to that length, it would head out this direction. Somewhere it would be long enough to connect capital C and some capital B lying along this side. So for these 2 cases, 1 triangle would exist. And here's a case where 2 triangles would exist, and that would be if sine of B, we're going to go with sub 2, is somewhere between 0 and 1. Using the sketch here, we can see that 1 triangle would use this as its third side, little a, but that same little a would also reach out to right here to B sub 2. So two possible triangles could exist. This one's easier to see with an example. Now, what if angle A was not an acute angle? If it were an obtuse angle, then 0 or 1 triangle could result. And we can see here in the table, this nice table lays it all out for us. Here, looking at the sketch, if this angle is obtuse now, okay, that's our situation. Given angle A is obtuse, we can see once again, lowercase a, this side length is too short. It won't ever be able to connect capital C and some capital B. And there's nothing wrong with that. It just means using your materials or your given measurements, you can't make a triangle. And then here we have where one triangle exists, and we can see that with an obtuse angle A, this third side length, little a, would connect capital C and some capital B lying along this side right here. So if angle A is obtuse, there is no option for two possible triangles. So just noting that there. These, this table right here is all for an acute angle A, and this table right here is all for an obtuse angle A. Okay, if that feels a little overwhelming, that's understandable. Let's see this in an example where A is acute and there are 0 possible outcomes. Okay, so we've got triangle ABC. Here's our situation. We've got an angle B measuring 55 degrees, 40 minutes. We've got a side length measuring 8.94 meters. And we have another side length measuring 25.1 meters. All right, 25.1 meters for one side length and 8.94 meters for another side length. Those are quite different. So we would need a very specific third side length that could connect those, and that would only be possible if this angle right here allows it, because this is also required. All right, let's see. Using these two ratios from the law of sines and plugging in what we know, we are trying to find capital A. Knowing little a, little b, and capital B, plug them in, and now try to solve for capital A. Use cross multiplication, divide both sides by 8.94, and it turns out that for this to be possible, sine of that capital A would have to be equal to this right here. Well, if you pick up your calculator and type this in, make sure you're in degrees, typing in from left to right, top to bottom, you're going to get approximately 2.3184379. For sine of angle A to be approximately 2.31 and so on, that's not possible. This is outside of the domain of sine. We know that sine bounces between +1 and -1, so since sine of angle A is greater than 1, it's impossible. There's nothing wrong with that. We just have the result that no such triangle would exist with this side length, and this angle measure. An attempt to sketch the triangle leads to this figure. Here we have our side length, 25.1. Here we have our other side length, 8.94. Here's our required 55 degrees, 40 minutes. And as we can see, it's going to be too short. There's no way we can get it to connect to this third side, making 0 triangles possible. Here's an example where A is acute and there are 2 possible outcomes. All right, here are our requirements. Angle A, 55.3 degrees. One side length across from that, 22.8 feet, and another side length, 24.9 feet. Let's pick the 2 ratios from the law of sines that include A and B, since that's what we are working with here, A's and B's. Setting it up like this, plugging in what we know, which is capital A, and little b, would look like this here. Cross multiply, divide both sides by 22.8, and this would be the measure of sine of B, or the value, sorry. Well, if we type this into our calculator, make sure you're in degrees, left to right, top to bottom, we're going to get approximately 0.8978678. This is in the domain of sine. Furthermore, sine of angle B hitting this value happens more than once. There are two triangles such that sine of B is equivalent to our 0.897 and so on. One option would be angle B being 63.9 degrees, and a second option for B would be 180 degrees less that, leaving us with 116.1 degrees. Sketching the first triangle, this first option right here. We have one angle measure of 63.9, the given requirement of 55.3, the two given requirements of the side lengths there, and we can see that this triangle can be constructed with those given measurements. Now let's check this one out. If B sub 2 is equal to 116.1 degrees, that would look like this here. Angle B sub 2, the given angle, the given two side lengths, and we can construct this triangle here. So this is a nice example of that case where two triangles could exist. I love this picture, the law of cosines. So we have very similar to the area of a triangle formula that we start with, 1/2 base times height. We do the same thing for the Pythagorean theorem. We start with hypotenuse squared is equivalent to one of the legs of the right triangle squared plus the other length, the length of the other leg of the right triangle squared. And we kind of, at first, when we're working and learning the Pythagorean theorem, we kind of just overlook this piece right here. But it is really the law of cosines that is holding up the Pythagorean theorem. Let me elaborate. Let's see. When we work with the Pythagorean theorem, we start with right triangles. So that would make theta right here 90 degrees. Well, we know that cosine of 90 degrees is equal to 0. So that would be this here minus 2ab times 0, making this equal to 0 and leaving us with the Pythagorean theorem in the form we first work with it. C squared equals a squared plus b squared. All right, let's look at the law of cosines in its entirety. In any triangle ABC with side A opposite angle A, side B opposite angle B, and side C opposite angle C, we have three possible forms of the law of cosines. Notice this one here, little a squared equals little b squared plus little c squared less 2, and then it takes these ones, their product, BC, times cosine of the included angle A. Here we have B, I'm not going to say the whole thing, just looking at the pattern, BAC, 2AC, cosine of B. And once more, CAB, 2AB, cosine of C. And everything I was rambling about up here with the law of cosines picture is noted for us here a little bit more formally, and that is if C is equal to 90 degrees in the third form of the law of cosines, then cosine of C equals 0, and the formula becomes the Pythagorean theorem. Example. A surveyor wishes to find the distance between two inaccessible points A and B on opposite sides of a lake. While standing at point C, she finds the labeled measurements. Find lowercase c to the nearest meter. All right, let's look at this figure. For some reason, we cannot get to point A, we cannot get to point B, and we would like to know the distance between them. So using this point C here, a triangle is constructed, and we know one side length, two side lengths, and one of the angles. And that is all we need to find all of the other missing parts of an oblique triangle. Okay, we are asked to find lowercase c. So strategically, we want to pick an equation that includes lowercase c, most definitely, and ideally it would only include lowercase b, lowercase a, and capital C as the other variables. We're going to pick one from the law of cosines, and there is one that has lowercase c, which that's required because that's what we are being asked to find, and the only other variables are little a, little b, and capital C. So this is perfect. This formula, plugging in what we know, 423 meters for A, 259 meters for B, 132 degrees and 40 minutes for C. At this point, we can pick up our calculator, type this in carefully, traveling from left to right. Be careful with your order of operations. If we type that in correctly, we'll get 349,510.5693, and then we'll need to take the square root of both sides. We are only interested in the principal or the positive root because we are finding a distance, and that will be approximately 628.10076 and so on, and that is in meters. So the distance between the 2 points is about 628 meters. Example, find angle B to the nearest degree for the truss shown in the figure. Okay, anybody studying engineering, you're going to have a lot of work with truss examples, and especially in your statics class. So what we've done is taken this truss right here, we've formed a triangle. We can see that it is an oblique triangle. We know the distance between our three vertices of this triangle. They are 6, 9, and 11 feet. And we are being asked to find angle B. So strategically, we want to select a formula that includes angle B, and ideally, the only other variables involved would be little a and or lowercase b and or lowercase c, because those are the other variables that we know. Picking from the law of cosines, this would strategically be the right choice. Little b, little a, little c, all known, and capital B is also included, which is required because that is what we are being asked to find. Plugging in the values that we do know and isolating cosine of angle B would give us cosine of angle B is equal to 11 squared plus 9 squared minus 6 squared, all over 2 times 11 times 9. When you type this in your calculator, be very careful and respectful of the order of operations, typing in from left to right, top to bottom, if you type that in correctly. And don't forget when you type it in that we need to move cosine to the other side, the equal sign, or we need to undo cosine rather, and that would be by using its inverse. So make sure to type cosine or arc cosine of this value that you get. If you do that correctly, you will get approximately 33 degrees. That would be this part right here. Heron's formula is for area, and that is if a triangle has side lengths A, B, and C, then the semi-perimeter, let's think of it as half the perimeter, because that's what it is represented by lowercase s, which is 1/2, and here we have the full perimeter, A plus B plus C. The area is, we use capital A for area, we're working with a triangle here, so this, in today's video, this is our 5th formula for the area of a triangle, and that is the square root of the semi-perimeter times the semi-perimeter less the length of A times the semi-perimeter less the length of B times the semi-perimeter less the length of C. Let's use this example. The distance, and that is as the crow flies, between cities is labeled. What is the area of the triangular region having these three cities as vertices? Round to the nearest 100 square miles. All right, so we have Los Angeles, Montreal, and New York. And these distances you see labeled are, it's sometimes called as the crow flies, or to beeline it. It means the shortest distance between the 2 points. So straight lines right here give us this constructed triangle, and we are asked to find the area of this triangle to the nearest 100 square miles. All right, so we need to select a formula for the area of a triangle. We have 4 just from today. We want to strategically choose one that includes capital A, because that's what we're being requested to find, and ideally it would only include lowercase c, lowercase a, and lowercase b. Well, if we choose this formula here, the only other thing it is dependent on is lowercase s. But lowercase s is only dependent on a, b, and c. So we can find the semi-perimeter, which is find the perimeter and half of that, giving us a semi-perimeter of 2,604.5 miles. Now that we also have lowercase s, this formula right here is ideal because it has the capital A we're being asked to find, little s, little a, little b, and little c, which we know all of those, so we can translate this geometric figure into an algebraic equation, which would look like this here. When typing this in your calculator, please be careful that your square root goes over the entire expression. Be respectful and careful with your order of operations. And if this is typed in correctly and then rounded to the nearest 100 square miles as requested, the area of the triangular region between Los Angeles, Montreal, and New York is approximately 401,700 square miles. All right, that finishes our discussion on Chapter 7. Please go to My Lab in Mastering and do the Chapter 7 homework now. My name is Jami Emigh. Thank you for being here, and I will see you next time.